Welcome to MEM09002 Interpret Technical Drawings. This lecture is a supplement to your student workbook and other resources made available to you. As a professional engineering tradesperson, reading and interpreting mechanical drawings is a critical part of your day-to-day activities. Student resources. If you haven't yet done so, pause the video now and download the learning manual for this unit, as it will be useful to complete the online quizzes and complete the practical assessment. You can download the learning manual and other resources for this unit from your Moodle account. Moodle is available for your computer or for your favorite mobile device. You will need access to a desktop publishing program like Microsoft Office. If you don't have access to Microsoft Office, you can download LibreOffice. It's available for all major operating systems and it's free. Same people that created LibreOffice created LibreCAD, which is a free 2D CAD or computer-aided design software package. LibreCAD has a AutoCAD feel and it's a great entry point for those starting their adventure in CAD work. If you have a Google account, you have access to Google Docs. This will enable you to create documents, spreadsheets, and slides and forms. It's free. You do need an internet connection, and you do get about 15 gigabytes of cloud storage. Google Docs is a free service. All the PerTech documents referenced in this tutorial are available from pConnect. All the componentry and adapters referenced in this tutorial are referenced from the PerTech product catalogs and the PerTech website. Whatever you're working on, good reference materials are critical to getting the job done efficiently and effectively. The recommended textbook for this unit is the Manual of Engineering Drawing. Check the resources section of Moodle regularly as we are constantly uploading reference material and documents. YouTube channel of the month is Cutting Edge Engineering. Colin from Cutting Edge Engineering takes you through the whole process of reconditioning and repairing hydraulic equipment. Main lecture. Whatever the task, we think, we plan, we do, and we review. It's the work smart method. In this lecture, we will be looking at identifying key information when interpreting engineering drawings. What is an engineering drawing? Let's have a look at the official definition. The definition of an engineering drawing is the art of drawing a picture of something that can be measured. You'll have to agree, some engineering drawings are works of art. We can liken an engineering drawing to a form of visual communication. When humans started to construct shelters or structures, some form of communication would have been necessary to describe what the designer had in mind. Although primitive by our standards, a sketch carved into a tree or an animal hide would have been just as effective as one of our modern paper drawings. It was Marc Isambard Brunel who proposed the first standardized engineering drawing. He was one of the great engineers of the Industrial Revolution and just happens to be the father of Isambard Kinder Brunel, one of the greatest engineers in history. What is a standard? What is generalized standardization? Let's look at the textbook definition of a standard. A standard can be thought of as an agreed upon norm used by people, industry, and government that outlines the best way to complete a task, whether it's about developing a product, providing a service, controlling a process, or interacting with the world. Well, what they're saying is, if we make things to a recipe or a standard, nuts, for example, made by one company will fit bolts made by another company because they're both using the same standard or recipe to make that component. Proposed standardization around the Industrial Revolution saw the birth of machine tools. Here we have pictured a screw cutting machine or a screw cutting lathe for producing nuts and bolts. Here we have a picture of some pre-Industrial Revolution nuts and bolts. Imagine having to forge, file, and chisel every single nut and bolt by hand. Without standardization and automation, the Industrial Revolution and industrialization would have not been possible. The standard we use for creating engineering drawings is the Australian Standard AS 1100. The standard defines every aspect of the drawing. Aspects of the drawing which include font sizes, layout of the drawing, sizes of lines, thicknesses of lines. As well as the textbook, another great resource for creating or interpreting engineering drawings is to get a copy of the Australian Standard. It's not surprising that there's a standard for creating engineering drawings. The Australian Standard is AS 1100. AS 1100 is a drawing standard that is used within Australia. It defines every aspect of the drawing. AS 1100 provides a standard that allows for clarity, understanding, and uniformity across all drawings generated nationwide. This AS 1100 standard didn't just pop out of the blue. It's mapped back to the International Standard Organizations, which is an international organization that ensures that drawings, irrespective of where they're created, can be read irrespective of what language the person speaks. You can purchase the Australian Standard from standards.org.au. Another useful resource is the Machinery's Handbook, as there's some cross-references to other standards. How do organisations ensure that they're adhering to Australian standards? Organisations will create a document called a Standard Operating Procedure, which is basically a series of steps or a formula to do something like create an engineering drawing, or create or manufacture a replacement hydraulic hose. There are a series of operations and steps to be performed to get the job done. There's sometimes confusion between the difference between SOPs, Standard Operating Procedures, and Work Instructions, or WIs. Standard Operating Procedures can be considered administrative tasks for documentation, and Work Instructions are practical instructions. Let's have a look at the engineering drawing. An engineering drawing is a type of technical drawing that is used to fully and clearly define requirements for engineered items. Types of drawings. We'll now look at three types of technical drawings that you'll come across in your day-to-day activities. We've got hand sketches, drafted drawings, and drawings created using CAD software. Firstly, we'll look at hand sketching. Freehand sketching in engineering is primarily used for describing concepts or communicating ideas, usually used in meetings or brainstorming sessions, or ideas scribbled on the back of napkins or envelopes and so forth. It's also commonly used in breakdown situations in remote locations where you have to quickly create a drawing and give it to the local machine shop. so you can get things made quickly, especially if you don't have access to the internet or your CAD or to your drawing equipment. The challenge of a hand sketch is to clearly describe the critical features and avoid communication and misunderstanding. You remember, you need to provide all the information needed to make the part in the case of an emergency breakdown. Manual drafting. This is the use of protractors and T-squares and drawing boards and various grades of pencils and so forth. The advent of CAD, computer-aided design, has basically superseded the need for manual drafting skills. Yes, it's still important to know how to use these tools. Third type, CAD software. CAD, or computer-aided design, is the use of computer-based software to create mechanical drawings. CAD software is particularly handy these days because we can go from a 3D model straight to an orthographic model or a 2D drawing of the component. CAD software is also commonly used for creating parts lists, assemblies, and 3D models. What type of information is communicated on a mechanical drawing? Is it a part or a part assembly? What views, what projections are there on the drawing? Are there quantities, materials, sizes, tolerances, or other special information on the drawing? An engineering drawing should contain all the information necessary to produce or assemble a component. As we already know, information on a drawing is displayed as per Australian Standard 1100. This ensures standardization and minimizes confusion. Here we have an example of standardization during the Industrial Revolution. Everybody's heard of the Whitworth thread. The Whitworth thread was the world's first national screw thread standard, devised and specified by Joseph Whitworth in 1841. Let's have a look at the drawing area. It's not a coincidence that the drawing area coincides with standard paper sizes. We are all familiar with the ISO page sizes, A4, A3, A2, and don't forget about the ANSI standards, the sizes A, B, C, and D. Another section of our drawing is the drawing area. This is where the component is located. As per the Australian Standard, part drawings need to be laid out in a certain way. In this example, the part is laid out in a third angle projection. It shows the front, the top, and the side view. With engineering drawings, when we view the part from multiple viewpoints, this is called orthographic projection. Imagine taking a cardboard box, unfolding it, and putting it flat on the table. You'd see all the views as an orthographic projection. Sometimes we can swap the positions of the views, and this is the type of projection. We have the first angle projection and the third angle projection, which are the common ones. The third angle projection, which is the most common internationally, except for Europe, we take the box, we unfold it, and we put it flat on the table, and this is our third angle projection. First angle projection, which is popular in European countries, it's the same as the first angle projection, but the left and the right views are swapped. First and third angle projections are the most common projection types in engineering drawings. Most of the world uses third angle projection, apart from Europe, which uses first angle projection as their standard. Sometimes parts need to be cut in half so we can see the detail. These are called section drawings. Do not scale is a common message on many drawings. Basically, even though a scale is specified on a drawing, do not measure the part directly against the drawing. Navigation marks. Navigation marks are also common on engineering drawings. They enable the location of key components from materials lists. For example, the location of the nut is at location 2E. Do not scale is a common message on many drawings. Basically, even though a scale is specified on a drawing, do not measure the part directly against the drawing. Navigation marks. Navigation marks are also common on engineering drawings. They enable the location of key components from materials lists. For example, the location of the nut is at location 2E. The drawing area will contain dimensions and specific tolerances. Specific instructions like fillet sizes and finishes can sometimes be included in the drawing area also. Some common comments that you'll see are remove all sharp edges, do not scale, if in doubt ask. Here's another example of a generic chamfer size, chamfers unless specified, 0.5 millimeters TYP, which stands for typical or unless otherwise specified. Tolerancing. Dimensional tolerance, which is commonly referred to as a dimensional accuracy, is the amount of permitted variance in the dimension of a part. This involves setting a maximum and minimum dimension limit for the part. Let's have a look at unilateral tolerancing. This is the deviation from a nominal size, but only in one direction. Here we have a nominal size of 15 millimeters plus 0.1 millimeter minus 0. So we have a unilateral tolerance. This can be specified as a plus or minus value next to the nominal size, or we can have a situation where we have the bottom and top size specified. Bilateral tolerancing is the deviation from nominal size in both directions. Here we have a nominal size of 15 millimeters plus 0.1 millimeter minus 0.1 millimeter. And that can be displayed in two ways, having a plus and minus tolerance next to the nominal size, or we have the top and bottom size specified. In this particular example, critical tolerances have been specified on the drawing. The dimension without tolerances will be dealt with the general tolerance specified in the title block. In this example, the 20 millimeter hole circled at the bottom has a unilateral tolerance stated on the drawing. The tolerance on the 75 millimeter distance circled on the left will be derived from the tolerance section on the title block. And in the title block, that 75 millimeters will have a plus or minus 0.15 millimeters in both directions, which that will be a bilateral tolerance. Sometimes the tolerance will be specified as an alphanumeric value from a limits and fits chart. This chart will be available online, or you can look it up in your copy of the Machinery's Handbook if you have one. In this example, we have a 20 millimeter H9 tolerance specified on the drawing. So the nominal size is 20 millimeters, and we look up the H9 value on the chart, and our new unilateral tolerance will be 20.062 millimeters and 20.00 millimeters. Okay, the 62 is micrometers, so it's 0.062 millimeters plus 0 minus. In our example, the H9 tolerance refers to a clearance fit on our limits and fits chart. If you're not sure what type of fit to specify on your drawing, again, reference it in your Machinery's Handbook. Now let's have a look at the title block. The title block. The title block is an area of the drawing that contains header type information about the drawing, like the drawing title, the drawing number, part numbers, name of the activity, the company's logo, organization's logo, etc. The title block also contains information on who created the drawing, who checked the drawing, what revision, what version number it is, When was it issued? The title block also contains information on the type of projection. We already had a look at that. The material and the surface finish. If we have a look at this particular specification here, cast steel. Oh, there's about 40 different grades of cast steel. In this situation, we haven't given the maker enough information. Again, this is where the if in doubt ask message on the drawing will come in handy. This will prompt the maker to contact you for clarification. Here we have the generic universal tolerances. These are the tolerances that you use if they're not specified on the main drawing. And here's an example referencing the drawing standard in the title block. Geometric dimensioning and tolerancing, GD&T. There are other types of information that we need to provide the maker, things like straightness, flatness, position accuracy, concentricity, surface finish, symmetry. Again, these are some of the symbols that you'll come across or use when you're creating an engineering drawing. Here we have an example of regular tolerancing combined with geometric dimensioning and tolerancing. In this example, we've got tolerances assigned to perpendicularity and to hole position. In this example, we have unilateral tolerancing, bilateral tolerancing, GD&T tolerancing. Although it would be unusual to have all three systems on one mechanical drawing, it's important to be aware that these tolerances can affect each other and need to be considered when manufacturing or assembling a component. The next question is, what are the standard requirements for the drawing? Sheet size, fonts and layouts, minimum information that I need to provide on that drawing. Features on a mechanical drawing can be described by different line types or line thicknesses. There are specific line types for center lines, for dimensions, for cross sections. Before the advent of CAD software, different line thicknesses were determined by what pencil you were using. Maintaining and sharpening all the different pencils was a skill in itself. Modern clutch pencils make the process of sharpening and maintaining pencil tips a lot easier. Electronic media and file formats. Each CAD software has its own proprietary file format. People or companies use different software for many reasons, like cost, tradition, features, familiarity, etc. You may want to share your 3D or 2D CAD designs with your customer or network for editing or CAM, computer-aided manufacturing processing. CAD file formats generally fall into two categories, either native, which is proprietary, or neutral, which are shareable file formats. In this case, both your software and the recipient software should understand the file format. This is where neutral file formats like IGES, STEP, STL come into play. Sometimes you want to share your files as a read-only. The PDF file is another form of electronic drawing. It can be easily produced and due to its optimized file size, convenient for electronic transfer and is protected from alteration. PDF files can be password and copy protected. Parts lists can sometimes be included on the engineering drawing. Here's an example of a parts list, and on the right hand side we have a parts list with a parts mapping location. So for example, part 9 is located at location A5. Modern CAD software enable dynamic listing of parts, for example, to a spreadsheet where parts can be dynamically updated and listed with the plug-in spreadsheet function. Version control. In engineering, version control is a process responsible for managing changes to CAD drawings. Changes are usually identified by a version number or an issue date. Become familiar with your internal version control system, as using an old, obsolete drawing version could have disastrous consequences. Remember, if in doubt, ask. Here we have some links to FreeCAD, Standards Australia, Machinery's Handbook, and Manual of Engineering Drawing mentioned in the presentation. Again, check with your local bookshop or favourite online bookstore for best deals on those.